University of Birmingham. He's a professor in surface engineering and one of the key partners in FIBRALSPEC.
Good morning, colleagues, ladies and gentlemen. I would like to use this short talk to share with you our recent research from FIBRALSPEC. So my talk will start with a short introduction to the topic. By way of example, I will give you some, our research and outcomes, and finish with some forward thinking. You are all experts in composites, so as we know, carbon fibers are widely used for composites because of the very high specific strength and stiffness, and the excellent oxidation resistance, corrosion resistance. So there are many applications in aerospace construction, or for energy applications. The major barrier to the further improvement in the performance in terms of the strength is the interface adhesion. This is mainly because, as you know, you are experts. For carbon fiber, there is a base planes which is from this graphic structure. This is a relatively inert surface, so that's the carbon fiber and the base planes. So that's one of the major reasons for the weak link for the composite, which is the interfacial shear strength. In addition to structure application, carbon fibers, especially carbon nanofibers, are also used in, for example, as electrode material. So here just to show you super capacity, it's double layer capacity. And very important for this application is the charge exchange between the electrode and electrolyte. So porous carbon materials, for example, graphene, carbon nanotubers, and the carbon nanofibers are materials of choice because of very large surface area if we make it porous and relatively good conductivity. However, if you do want to improve the performance further, then we need to improve the conductivity and some other performance or function as well. So there are many different types of surface treatment methods. Broadly speaking, they can divide into two major groups. The first is based on wet or electrochemical treatment, as shown here as an example. This is a very flexible process, relatively cost-effective. The only concern is the environment and potential damage to the carbon fiber surface if we use quite some acid. On the other hand, it's a dry process. You can use gases, you can use plasma. So for wet process, yes, you can change the surface chemistry. However, it is difficult, if not impossible, to change, to improve the inertness of these base planes of a carbon fiber surface. And the plasma process can do both to confer the functional group to the surface. You can also change the surface inertness of the carbon fiber. So here just show two examples. For example, we can use atmospheric treatment, or you can use a low pressure plasma. One thing in common for these two plasma technologies, carbon fiber being treated are directly exposed to plasma or discharge. Okay, so it's good, it's effective, but potentially you may also, to some extent, damage the carbon fiber surface. So in my talk, I would like to introduce some plasma technologies we developed in Birmingham. So the first one is active screen plasma surface activation of carbon fibers. We are all familiar with the DC plasma, which can be used or widely used industrially to improve the performance of metals and alloys. For example, the RPAs are being treated in a DC plasma. However, this technology cannot be used to treat carbon fiber. So recently, we use so-called active screen plasma. So the main difference between DC plasma and active screen plasma is that we install a matte mesh screen in the furnace. And then the table is at floating potential, and the matte mesh screen is biased, is an anode, a cathode, and the wall of furnace is an anode. So plasma will forms on this matte mesh screen, we call it active screen. There's no plasma on the parts being treated. So this is a major advance in plasma technology. So you can treat not only conductive materials, but also non-conductive materials, such as polymer or ceramics, and here we're talking about carbon fiber. So here I'll just give you an example. So we use active screen plasma, and the gas we use is 75 hydrogen and 25% nitrogen. Of course, we also use some other gases. Here, just give you an example. And the treatment time could be a few minutes to half an hour. Normally, no more than half an hour. Okay. So this is what you can see from the observed window. So plasma forms on this active screen, and the carbon fiber is inside the active screen. So in essence, this is a post-discharge treatment, not directly exposed to plasma itself. Later I will show you the enhancement of the performance is related to the post-discharge rather than direct plasma. Okay, so let's look at some, the change of the surface chemistry. So this is our survey spectrum. On the left-hand side is for untreated or as received carbon fiber. On the right-hand side is active screen plasma activated carbon fiber. You may have noticed the peaks looks very similar. That's true. The major difference is you can see if you look at nitrogen 1s peak and then following active screen plasma treatment, the intensities increase. So it implies that you introduced nitrogen-containing functional group to the surface of plasma-treated carbon fiber. We have done some more high-resolution spectra, and then if you compare these two, again, left-hand side is for untreated, and the right-hand side is the active screen plasma treated. So if you look at the intensity and the shape of these peaks, there are significant change, especially for peak 3 and peak 4, if you can see the intensity change is significant. So that means the surface chemistry has been changed by active screen plasma treatment. In order to understand what happens for the change of surface chemistry, we also have done optic emission spectroscope. Try to identify what are active species they have contributed to the change of the surface chemistry of this carbon fiber. So this is a typical spectrum we collected. So you can see, of course, the nitrogen ion and some other active species, N2 star and H. Of course, it contains 75% hydrogen, so you can also see hydrogen. So what's the connection between the active, the species and the change of surface chemistry? So this chart give you a hint of nitrogen content from XPS. That's the OES, is optical emission spectroscope intensity. So most people believe it is nitrogen ion contribute to the change of the performance. That's true maybe for direct plasma treatment. However, for our active screen plasma treatment, as you can see, when you change the voltage, you change the OES. However, the OES signal is almost no change. Okay, so it is not nitrogen ion, but some other active species, so N2 star or NH. So you can see the correlation between the nitrogen content and the OES intensity. Okay, how about surface morphology? Because we use post-discharge plasma. So as shown on the screen, on the top is high resolution SEM, and the bottom is AFM. So yes, you can see very minor change to the surface morphology, and the surface roughness is increased from about 6.3 to about 10. However, is that there's no major changes, no arcing damages to the surface. How about the backability? That's very important or ultimate target for us, right? So we use, of course, we use the water and some other solutions, but most relevant the backability is to resin. So we did resin, and this chart just summarizes the contact angle and for different treatments. So again, this is the contact angle of untreated carbon fiber is 52, and when you change either the gas content or others, or treated carbon fiber shows much lower contact angle and improve the battability. Right. Now let's look at the effect of this plasma or active screen plasma treatment on the strength of the single fiber. So this chart just summarizes some parameters and some carbon fibers we treated, just as an example. So of course, for some carbon fiber, for some parameters, you can see here, you slightly reduce the single fiber tensile strength. However, for these three, you can see here, actually, there's no loss or slight increase, or for these two, for this one, as more significant increase in the strength of a single fiber of active screen plasma treatment. Okay, this may be mainly because there's no surface damage to the carbon fiber because of the post-charge treatment. Of course, for these two, as you can see here, the top, there are slight reduce of the strength. Then if we look at the change of the diameter, yes, there's a correlation between the loss of the strength and the change of the diameter. So we do need to carefully control the treatment parameters, otherwise you end up reduce the strength. The tensile strength of microplastics use untreated carbon fiber and the treated carbon fiber. This is a carry-on work, and of course, for some treatment, there's no significant change of the strength, tensile strength. But for one carbon fiber, actually, that before the treatment is the tensile strength is 1060 above something, and then increase to about 2000 megapascal. So the improvement is more than 25%. This work has been published recently in Journal of Vacuum Science and Technology with Professor Charitis and Paritis in NTUA. And actually, our case has been used as a cover page. Okay, so let's move on to the second example. Is the truck glue plasma surface functionalization of carbon nanofibers. Right at the beginning, I mentioned for high performance supercapacity or for other electronic applications, we do need to improve the performance of electrode, especially electrode materials. So, if for active screen, of course, we can use active species to activate the surface of carbon fibers, but here we are more focused on improving the electrical conductivity of carbon nanofibers. So we do need to introduce some nanoparticles onto surface. So in order to achieve these targets, we developed a more advanced plasma technology that's called tropical plasma. So if we ignore the cathode 2 is the same active screen plasma, however, we introduce a second cathode. So plasma can be formed on the screen, on the source. So it could be silver, gold, platinum, or some other materials. Okay, so here I would like to show you some, carbon nanofibers of the tropical functionalization treatment. Maybe it is a bit difficult for you to see at the rear, but I can clearly see or say there are some nanoparticles, and it depends on the elements you want to use. Some are very fine. For example, for platinum, is really you can see here. But I can tell you the size of the platinum particle is 20 nanometer. On the other hand, for example, for PD, and then it is about 250 nanometer. So you can see particles cover the whole surface of carbon nanofibers. This, of course, can see the size of particles. To some extent, they are related to the yielding of the material, the element. However, the order is slightly different. That means treatment condition has played also an important role in the formation of nanoparticles in terms of the size and the coverage. This is a TEM picture, shows clearly the nanoparticles on the surface of this nanocarbon fiber. So the size it could be 10 nanometer or 50 nanometer or up to 200 nanometer. Okay, so what about the performance? Yes, we use the 3 electrode cell to conduct a cyclic voltammetry test. This is mainly because this is the equipment we use. So after the test, you can, as the name indicated, this is the current against the potential you applied. So the specific capacitance, Cs, is the integration of I times dV. That's the area of this curve. And so in this way, we can clearly see here, for example, this is the curve, this is the curve for untreated material in the middle. So the area is very small. However, after silver surface multifunctionalization, the area has been significantly increased. That means the capacitance can be improved. So these charts summarize the increase of the capacitance as a function of the surface treatment. So this is the carbon nanofibers without surface treatment. And then if you apply different tropical plasma functionalization treatment, and then you can see the capacitance has been significantly improved. Of course, it depends on the treatment conditions and the element you use. So these results have been recently published in SS Applied Material Science and Interface, and you can find more details from this paper. Okay, this is joint efforts, so the paper is published by Birmingham and NTUA, and Professor Charitis is one of the co-authors. This is more up-to-date work, and last week I received the electrode made by TRT, is one of the key partner of our FIBRALSPEC. Okay, so this is, on the left-hand side, is use 20% untreated carbon nanofiber. On the right-hand side is platinum-treated carbon nanofiber. It's a different color. The color is slightly different. Oh, I can tell you, yes, we can successfully use dynamic spray gun to produce a larger area, 5 centimeter by 5 centimeter electrode. So Polo is testing these two electrodes. Okay, so what's next? Yes, we have shown some quite positive results from laboratory. Okay, however, there's one step forward is for application, right? As a scientist, it's always satisfaction if you can see the successful application of your technology. Okay, so there's some idea put here. That means how can I make the results from TRL4 we achieved now and to TRL6 or 7? So I have to admit that there's some limitation for our TRL4 results. For example, for the treatment for active screen plasma activation of carbon fiber, currently is a batch process. So we can treat a segment 100 meter is not a continuous process. Okay, so one idea is we try to introduce some device into our furnace, then we can achieve lower to lower continuous achievement. So this is the active screen plasma. That's for carbon fiber treatment. Very similar. This is carbon nanofiber. Currently, it's a batch process. So how can we treat more and cover the whole surface? Because one comment from the reviewer is that how can you cover the whole surface, right? So one idea is we can design a tambourine device. So during the treatment, this container can tilt. In this way, you can cover the whole surface of the carbon nanofiber. Okay. All right, so that's all. Thank you for your attention. But more important, I would say, I would thank EU for the financial support to this project. Without this support, I don't think we can achieve anything. So really, I thank the European Commission for the financial support. I would also thank to our FIBRALSPEC consortium, especially Kostas. With his leadership, we have achieved quite a lot. So what I introduced, just one or two small examples from this very successful project. Finally, I would like to thank the team members in Birmingham for their work. So my contribution is just present the results. Okay, thank you all.